Welcome back, guys. In this video, we're going to discuss the differentiability of functions of 2 and 3 variables. We'll discuss how differentiability is different for functions of several variables than it is for functions of a single variable. We'll define differentiability for a function of 2 variables and a function of 3 variables. We'll discuss when we can use differentials to approximate our functions, and I think I'll just give it away right now. We can use differentials to approximate our functions when the functions are differentiable. We'll show that a simple function is differentiable using the definition, and then we'll say in general that it's pretty difficult to do using the definition. So we'll provide some sufficient conditions for differentiability, or a sufficient condition for differentiability for functions of 2 variables, and then we'll extend it to functions of 3 variables. Okay, so differentiability is different with functions of several variables because in Calculus 1, when we said the function was differentiable, we just meant its derivative exists. And maybe we're saying it's differentiable at x equals x naught. That just means that f prime of x naught exists. And that's good enough. In Calculus 3, partial derivatives existing is not a guarantee of differentiability. So let me write that down. So partial of f with respect to x at x naught y naught. Partial of f with respect to y at x naught y naught. The fact that these exist this does not necessarily imply differentiability. So are those equivalent? No, that's not enough to say that. And the same is true for functions of 3 variables and variables. Just having a bunch of first partials that exist at a certain point does not mean that the function is actually differentiable at that point. So we're going to define differentiability differently. This is how we'll define it for functions of 2 variables. We'll say that z equals f of xy is differentiable. We say that this function is differentiable if delta z, that's the increment of z, may be written in this way. If delta z can be written as the partial of f with respect to x at x naught y naught times delta x plus a function of f, or the partial of f with respect to y at x naught y naught times delta y plus epsilon 1, it's just a function that may depend on x, y, delta x, delta y times delta x plus epsilon 2, which may be a function of x, y, delta x, delta y times delta y. If our function, or if the increment of z can be written this way, where epsilon 1 and epsilon 2 approach 0, so these are functions of x and y, but these approach 0, x, y, delta x, and delta y, as delta x and delta y simultaneously approach 0. if we can do this, then we say that z is differentiable. And you're like, oh my gosh, what? Well, let me give you a concrete example of this. So let's say our function is z equals x cubed. Now let's just do x squared, make it a little easier on ourselves. X squared minus 3x times y squared. So that's our function of two variables. And we want to show that z equals f of xy, where this is f of xy, is differentiable. For all xy in the xy plane. So all xy in R2. Any xy you want, this function is going to be differentiable. Well, in order to show that, I need to show that the increment, which we defined earlier in the last video, can be rewritten this way. So that's going to be the partial of f with respect to x at x naught y naught, plus the partial of f with respect to y at x naught y naught, plus this, and we're saying that this is z equals f of xy is differentiable at x naught y naught if all of this is true. We want to show that this is differentiable for all xy. So instead of having x's and y's here, I want to have instead of having an x naught and y naught here in each of these partials, I want to have an x and a y. Okay. So we want to show that this function is differentiable at all the xy in the xy planes. That means we need to be able to rewrite delta z this way. Now this is going to be evaluated at xy, and that will be evaluated at xy, and then we have this over here. Okay, so the way you start this is you start by writing down the increment of delta z. Actually, I think I want to start by computing those two partials. And then we'll write down the increment of delta z. So compute the partial of z, or f, with respect to x, and the partial of f with respect to y. Okay. So if this is z sub x is the same as the partial of f with respect to x. That's just 2x. And this is a constant times x as far as we're concerned when we're differentiating with respect to x and treating y as a constant. The derivative of a constant times x is just the constant. Partial of z with respect to y. This part, there's no y in it, so it's 0. Partial of this part with respect to y, negative 3x is a constant, and we differentiate with respect to y. So we bring the 2y down and we get negative 6xy. Okay, so we've computed those two partials. We know that that's what we have to have in front of our delta x and in front of our delta y once we've rewritten the increment. So we've computed those. Now we want to compute and simplify. Basically, we're going to rewrite the increment delta z. And remember, this is the z final minus z initial. And z final is f of x plus delta x, y plus delta y. Z initial was just f of xy. So we want to simplify this and show that this can be written this way. Okay, so we've already done that first step. That was step 1. We computed the partials, so we're done with that. And now we want to calculate or compute partial of f with respect, or delta z, excuse me, the increment of z. So I need f evaluated at x plus delta x, y plus delta y, minus f of xy. So this is my f. So I'm replacing the x with x plus delta x. I'm replacing the y with y plus delta y. So this is going to be a bunch of algebra. Don't be intimidated by it. It's just algebra. It's just distribution. So there's our f of x plus delta x, y plus delta y. and then we'll subtract, don't forget your big old parentheses, we're subtracting the whole thing, f of xy, so that's this guy right here. Okay, so now I've got to simplify this and eventually try to make it look like that. So if I write that twice in FOIL, I get that. First times first is x squared. Oops. Outer times outer is x delta x. Inner times inner is another x delta x. Last times last is delta x squared. Then we'll have a negative 3 times this. And this one can be rewritten as y plus delta y times y plus delta y. If I FOIL that, I get y squared plus 2y delta y plus delta y squared. Just first times first, outer times outer, inner times inner is the same, and last times last is that. And you're like, whoa, my goodness. No big deal, guys. It's just algebra. It's just a bunch of distribution. Distribute the negative 1. Okay, and keep going. So I'm on the next page. That's all right. No big deal. I've got this trinomial times a binomial times a constant. So I think what I will do, oh look, I get a cancellation already. Boom. Always nice when it simplifies even a little bit. Grateful for the little things. So this is what I'm going to do here. I've got a binomial times a trinomial. So I'm going to take this x, and I'm going to multiply it by all 3 of these guys and the negative 3, and I'll write that down. And then I'll take delta x and I'll multiply it by all 3 of these terms and multiply by the negative 3 and write that down. So let's do x times all of this first. Actually, I think I'll just write it down. I have negative 3x times the trinomial. And then I have minus 3 times delta x times the same trinomial. You're saying, oh my goodness. Yes, me too. Plus your 3xy, or 3xy squared. Okay. Keep going. And remember what it means to be differentiable. I'm going to fold my paper. Oops. With my definition of differentiability on it so we can see it. It's like we've got a goal in mind. This is what we're going for. We're going for this right here. We just need to be able to rewrite the expression we have, this ugly thing, which represents the increment of z. And we need to be able to write it this way. I keep folding until all we can see is that beautiful vision, that goal that we have for ourselves. That's the goal. And I think I'll highlight it as well. This is what we're after. Okay. It's keeping it in place with this coffee cups. All these coffee cups that I've got around here. Okay. So, more algebra. Let's distribute the negative 3x. So negative 3x times that is that. Negative 3x times that is this. Negative 3x times this. Same thing here, but the negative 3 times delta x. want to put the delta x at the end. Plus the 3xy, I keep saying xy, 3xy squared. And look, get another cancellation. That's cool. Very nice. It's very good because I don't see any functions of x that don't have a delta x or delta y multiplying them. And it looks like we don't have any functions of x without delta x or delta y multiplying them. That's a very good thing. Okay, so this is our expression, and we need to rewrite it like this. We also need to remember those two partial derivatives of f with respect to x and y. So we're supposed to have, I'm just going to look at the paper for us. I'm going to say recall what partials of f with respect to x and y were. The partial of f with respect to x was 2xy, or excuse me, 2x minus 3y squared. And the partial of f with respect to y was negative 6xy. Okay, we're back. So I need that times delta x and negative 6xy times delta y. Do you see it? Hey, there's a 2x times delta x. That's that first term, because I need this times delta x. So I have a negative 3y squared times delta x. Hey, there it is. So I'm going to group those two guys together. Factor out the delta x, 2x minus 3y squared times delta x. And there's that first guy. Yay, I'm very happy. Awesome. And then we've got this next one. We need a negative 6xy times delta y. And there it is right there. So I've got minus 6xy times delta y. So far so good. Now I need a function of xy, delta y, times delta x, plus a function times delta y. Ooh. Well, there are a lot of them. Let's see what we've got. I've got a delta x squared and here I have a negative 3x delta y squared and here I have a negative 6y delta x delta y. So I took care of that and that and that, and then this one has the delta x and the delta y squared again, minus 3 delta x delta y squared. Okay, now epsilon 1 and epsilon 2 are allowed to be functions of x and delta y, or x, y, delta x and delta y, but they have to go to 0 as delta x and delta y go to 0. Like, that's our goal. So yeah, I need to bring everything together that just has, let's just group everything that has a delta x in it together. Well, no. Remember what our goal is. This has to be something that's going to 0 times delta x. So this has to have a bunch of factors that have either a factor of delta x in them or a factor of delta y. So that when delta x and delta y go to 0, I've got something that's going to 0 as these guys go to 0. So with that in mind, I am going to group this way. Just writing down the other stuff, not really doing anything with it. That needs to be there. And then I need delta x times something that's going to 0. Delta x times one more delta x gave me that term. Now, there is no delta x in that term. That's okay. That can be handled by the delta y, so we're good there. This one has a delta x in it, and if I factor that out, I'm left with a negative 6x times delta y as delta y goes to 0, the rest will go to 0. So I will put that here, negative 6x delta y. And then this one has a delta x in it. And if I factor out the delta x from here, I'm left with a negative 3 times delta y squared, as delta y goes to 0, delta y squared goes to 0, so that will work. I can put that in over here. Negative 3, I didn't quite leave myself enough space, times delta y squared. Sorry guys, it looks bad, but that's just negative 3 times delta y squared. Okay, so I've got all those guys, and then can I write this one as delta y times something that's going to 0? Say yes, factor out a delta y there, and you're left with a negative 3x times delta y. If you're saying to yourself, Ms. Townsend, why are you doing that again? What was the point of that? Why did you have to have the delta x and the delta y in just this way so that, why are you doing that? What I'm trying to get is a function of x, y, delta x and delta y right here, times delta x, plus a function of x, y, delta x and delta y times delta y for right here. I'm trying to get all of those, and it looks like I've got them. Okay, so this is my epsilon 1, and this is my epsilon 2. Now, in the limit, as delta x and delta y both go to 0, epsilon 1 has to approach 0 and epsilon 2 has to approach 0. So we'll take the limit of these guys. Epsilon 1 was delta x minus 6x delta y minus 3 delta y squared. As delta x goes to 0, that's 0. As delta y goes to 0, that's something times 0, so that's 0. That's 0 squared times 3, so that's 0. And so we get 0. So as delta x and delta y go to 0, both of them individually, epsilon 1 goes to 0. And we have to show the same is true for the epsilon 2. Oops. Let's look at that. As delta y goes to 0, well, this is 0 times something, so we get 0. What was all that for? Okay, remember, we said if we can write delta z as the partial of f with respect to x times delta x, plus the partial of f with respect to y times delta y, plus delta x times something, plus delta y times something, and those somethings, the epsilon 1 and epsilon 2, have to go to 0 as delta x and delta y go to 0, and they do. If you can write delta z this way, then your z is differentiable. So that means the function that we started with, z equals f of xy, which was x squared minus x y squared, 3xy squared, excuse me, that is differentiable for every xy. So not only do the partial derivatives exist, but the function is differentiable. And what it means when we say the function is differentiable is that it means we can use that tangent plane that we came up with earlier, that linearization of the function, and it's going to be a good approximation. I promised you at the beginning of this video that we would talk about when we could use the differentials as approximation to the function. And this is it. If the function is differentiable, the tangent plane is a good approximation to the function near the base point, near that x naught, y naught where you started. I'm going to write the tangent plane approximation. I'm going to write near p because we want this to extend to functions of 3 variables and functions of 5 variables and functions of n variables. So you can come up with this linear approximation. It's a tangent plane when our function is a function of 2 variables, or a tangent plane when you're dealing with a level surface of a function of 3 variables. But we can come up with a linearization or a linear approximation of any function of n variables, doing a generalization of what we've talked about in the last few videos. So now that we know about differentiability, if your function is differentiable, so if the function can be written in this way that we've just talked about, then the tangent plane is going to be a good approximation to the function near p, and if the tangent plane is a good approximation, that means it's a good idea to use those differentials to approximate the function. So that means dz is a good approximation to delta z. So that differential of z, evaluated at that base point x naught y naught, is a good approximation to delta z, the increment, the actual change in z, provided that, or if, the original function is differentiable. Okay. You may be saying, okay, well, what does this really mean? It feels like a bunch of algebraic manipulation, and you're like, I think I might be able to do it, but what am I getting at here? What we're getting at is the derivative exists, or not the derivative exists, the derivatives in all of the directions exist. It means the function is going to be nice and smooth near your point. It means the tangent plane is a good approximation. If there are no strange folds in the surface, so you don't have a limit in one direction that's one value and a limit in another direction that's a different value. So all the limits exist. The limit as x naught y naught approaches that point, it exists, and it's equal to that function value. So the function's continuous there. And not only that, but like the derivatives in all the directions are continuous. Like it just works. If this is true, then basically our function is nice and smooth. And if it's nice and smooth, that means the tangent plane is a good approximation. That tangent plane that was given in the formula earlier, that's going to be a good approximation to the surface. And if the tangent plane is a good approximation, this differential dz is a good approximation to the actual change in z. Okay, so I also promised you that in this video we would talk about differentiability of functions for functions of 3 variables. And I bet you can guess if w is a function of x, y, and z, well, if delta w can be written this way, partial of f with respect to x times delta x, plus partial of f with respect to y times delta y, plus the partial of f with respect to z times delta z, plus something times delta x plus something else times delta y plus something else times delta z. And these are functions of several variables themselves, epsilon 1, epsilon 2, and epsilon 3. If epsilon 1, epsilon 2, and epsilon 3 approach 0, all 3 of them, as delta x, delta y, and delta z approach 0, then w equals f of x, y, z is differentiable. So if we can write the increment of w this way, so that means as our changes in x, y, and z get very small, this whole thing gets very small, and then this is going to be equal to this, then we say our function w is differentiable. I'm not going to do an example like that. I just wanted to show you the idea. The same is going to hold for functions of n variables. It's going to have exactly the same form. Okay, Now, you might be saying to yourself, I have no desire to do that ever again, and I don't blame you. There's got to be an easier way, you may be saying, and there is. We've got what's called a sufficient condition for differentiability. Okay. If f is a function of two variables and the partials of f with respect to x and y are continuous in an open region R, under those conditions, then f is differentiable on R. Wow, isn't that nice? All you have to do is take the two partials, if they exist and they're continuous, on an open region. That just means like some region not including the boundary. Okay, so that's R in the xy plane. If those partials are continuous on a region that looks like that, f is differentiable on that region. If there's any x, y values that cause those partial derivatives to be undefined, like maybe there's a 0 in the denominator along some value of x, or on some line or some curve in the xy plane, issues with logarithms and square roots, all of those things that we have had to worry about before with continuity, then your function might not be continuous there. But this says as long as you stay away from those problem areas and the other areas that don't include the problem areas, but all of those other points, the function is going to be differentiable there. As long as those partials exist and they're continuous, then the function is differentiable there. A function of three variables is similar. So this is z equals f of x, y. It gives us a surface. Now I can't graph this one because the graph of this would live in four-dimensional space. All we can do is graph level surfaces, let w equal a constant, and then we get a corresponding surface. If w is a function of three variables and all three partials, first partials, are continuous, on an open region R, and this time, because our function is a function of three variables, R is a subset of three-dimensional space, then this time this function f is differentiable on R as well. So W is going to be defined for regions in three-dimensional space. So maybe we're talking about like a ball that looks like this. Maybe the interior of that is the region R. So it's like a sphere, but we're talking about the inside. If all three of those first partials are continuous there, we're good. Now this is sufficient. Sufficient and necessary are two different things. This says if this is true, we're guaranteed it's differentiable. Now these do not necessarily have to be true for the function to be differentiable, but if they're true, we're guaranteed differentiability. So usually we'll just check that rather than using those definitions that we talked about. So guys, that's what it means for a function of several variables to be differentiable. And again, if a function is differentiable, then it's okay to use the tangent plane as an approximation to the function. And if it's okay to use the tangent plane as an approximation to the function, then it's okay to use the differential to approximate the change in z. Now, I talked about differentials of z. Let's talk about differentials of w. Differential of z is this, where z is a function of two variables. If I evaluate at a point, this gives me the expected change in z using the tangent plane at that point to approximate the function, provided x changes by delta x units and y changes by delta y units, and delta y and dy and delta x and dx are the same thing. So that's how we interpret that. Now, if w is a function of three variables, we can also calculate its total differential. It has three variables, so it's the partial or the total differential will have three terms. And again, if we evaluate at x naught, y naught, z naught, that's going to give us the approximate change in w using the linearization of w. It's going to be a hyperplane to approximate w. And we can use that hyperplane to approximate w. This would be a good idea to use that when x changes by delta x or dx units, y changes by delta y or dy units, and z changes by delta z or dz units. That would be, then in that case, if w is differentiable, it'd be a good idea to use this as an approximation for the change in w as you go from that base point x naught, y naught, z naught to a nearby point. So that's differentiability, guys.